Okay, so here's a standard torque problem. We're given the mass of the bridge, and then we're given dimensions for where everything occurs, and we're asked what the tension is. In this problem, I've marked all the forces that are acting on the bridge. I'll highlight the actual bridge so we see that a little more clearly, what we're looking at. That's our object of interest. Now, we have to identify this as an equilibrium problem. How would I know it's an equilibrium? Well, it doesn't say the bridge is falling. And so we make the logical assumption, hey, the bridge isn't falling. It must have an acceleration of 0 and an angular acceleration of 0. Hence, the net force is 0 and the net torque is 0. Now, an important thing to remember is that's the net torque about any point is 0. I could choose any point at all. It doesn't even have to be on the object. But if I find the net torque acting on the object, it's going to be 0 from any location. And so now I simply need to determine what's the easiest way to find the force of tension. Now, if I look at this, I have 3 unknowns. So let's talk about what we know and what we don't know, because that identification of unknowns is really important. We know the force of gravity vector is equal to mass of the bridge times g down. So our direction is down. Put the little unit vector sign for it. So we know 2 things about it. We know its magnitude and its direction. We know all the dimensions. So that means we know the force tension is in the direction that's shown, which I can calculate using B and C. So if I call that angle theta, theta is going to be, I know the opposite side and the adjacent side, so that would be arctangent, or tangent to the -1 of the opposite side C over the adjacent side B. So I know the direction of the force of tension, but not its magnitude. Now, what do I don't know? What do I not know? I don't know the force of tension magnitude. That's what I'm looking for. Mm-hmm. I don't know the force of the hinge magnitude or direction. So there are 3 things I don't know. So, typically, you would go ahead.
Would you sum it about like the hinge?
That's right. Typically, you'd say, oh, well, I'm going to have 3 equations because I have 3 unknowns. But if we sum the torques around the hinge, why would you do that? You're exactly right. So I assume you know why.
Because then you only have 1 variable.
Right, because that's going to make it torque is R cross F. Mm-hmm. And so I'm going to have the radius for the hinge is 0. Cross product to force hinge, I'm just going to put 0 times force hinge because that's 0, right? Mm-hmm. And don't have to worry about its direction. Let me get rid of the vector sign. I'm going to sum them in the direction coming out of the screen. So I have that for the first one. And then for the force of gravity, is that going to make a positive or negative torque about the hinge?
Negative.
It's going to be negative because R cross F, like we had on 2 tests ago, I guess. Mm-hmm. The R is going to your right, the F is going down. So index finger, the right hand to the right, orient your hands, your middle finger can point down, your thumb points into the screen. That's negative. So minus, now that distance is going to be L over 2 minus A. And A I gave was L over 10. So L over 2 minus L over 10. Times mass of the bridge times G. And then finally, this force here, the distance from the hinge point to where that acts is B. It's going to be a positive for the right-hand rule again. And B had a magnitude of 2L over 3. So 2L over 3 times the force tension. If it's in equilibrium, we establish the sum of the torques is 0, so that's equal to 0. And now I'm able to right away calculate force of tension is equal to, L over 2 minus L over 10. Common denominator is 10. 5 minus 1 is 4 tenths. And so that's 0.4 mbg. And then I had to divide by 2L over 3, which is the same as multiplying by 3 over 2L.
Why would you have to divide?
Oh, and I forgot. It's 0.4 L. Because I'm solving for force. Okay, doing too many steps at once.
Mm-hmm.
I was looking at the clock and trying to hurry for you. So just moving this across for the first step, I have 2L over 3 force tension is equal to, let's put 2 over 5L, right? Because L over 2 minus, that was 4 over 10, which is 2 over 5L mbg. And so then I want to solve for Ft, so I have to divide both sides by 2L over 3. And that gives me force of tension equals, notice the 2L's are going to cancel. So force tension, and of course this canceled.
Good, how are you?
Can we go over really quick? Maybe I should do it after class, but I wanted to go over the motorcycle one again. That question with the right hand rule. It was like 2 tests ago, and it was like,
oh, sure. I understand what you're saying.
Yeah.
So in that problem we had, let's look at a top view first.
I just don't know if we can do it in 2 minutes.
Here's the motorcycle traveling with a, the purple looks a lot like black, at least on my screen. Velocity like this. So the front tire is rotating, and that rotation is giving it, using the right hand, an angular momentum that's going like that. So that's what we see from the top. Now, if we look at a side view, or let's say a rear view. So now we see, here's the back tire. The front tire is right in front of it, so we can't tell the difference. If it's traveling away from us, right, rear view means it's traveling away from you, then that means that we have our angular momentum is still going to be pointing that way. It's going from top, just rotated it, it's still pointing to the left. So our angular momentum's to the left. But now we're going to have it tip. So having it tip, it's now like this. And of course, the angular momentum would have to point that way if it's tipped. And now we're calculating the torque. And it asks for the torque created by the motorcycle about the pivot point. So I want the torque about this point. So we have the force of gravity is acting here. And the radius for that force is like this. So using the right hand rule, index finger needs to point in the direction of R, or your hands and middle finger can point in the direction of F.
Wait, R is here.
R is pointing like that. And then the F is pointing down, and your thumb points into the screen. Yeah. And so that means that the torque is forward. So if I come back to this picture, my torque is like that. Right. And then for final, change in angular momentum. Well, start with this, Newton's second law in rotational form. Net torque is equal to change in angular momentum over change in time. So you solve that for change in angular momentum is equal to the net torque multiplied by the change in time. So the change in angular momentum is the same direction as the net torque.
I gotta go to class, but can we maybe go over that a little slower? like after class?
I'd be happy to.
Okay, cool. Thank you.
Yep.